It looked like a footprint in gray ash, but when the astronaut reached down to brush it off his boot, it didn't move. It clung. It had worked its way through 3 layers of material in less than 72 hours, and nobody had warned him it could do that. That detail, that one quiet detail, is the reason some scientists now believe we should never send humans back to the moon. I'll explain exactly why at the end of this video, and I promise the answer is so much stranger than you think. But first, quick question before we dive in. Where are you watching this right now? Drop it in the comments. I genuinely want to know. 3 a.m. in your bedroom? Lunch break at work? I'll be reading them. We have been told a comfortable story about the moon our entire lives. It's right there, every night, hanging in the sky like it belongs to us. We've walked on it, we've driven a rover across it, we've hit a golf ball into its dust and laughed about it. 12 people have stood on its surface, and every single one of them came home. So it feels safe. It feels small. It feels like something we already conquered 30 years ago and just haven't gotten around to revisiting. None of that is true. Because the 12 people who walked on the moon, they were never there long enough to find out what the moon actually does to you. The longest any human being has ever stood on the lunar surface is less than 3 days. 3 days. And what we've learned in the decades since they left, from the samples they brought back, from the satellites orbiting it right now, from research published just months ago, should change everything about how we think about going back. The problem starts before you even open the hatch. Every single Apollo crew reported the same thing: the dust. It was everywhere. It coated the suits, scratched the visors, jammed the equipment, and clogged sample containers that had been engineered specifically to seal tight. When the astronauts tried to wipe it off, it clung harder. When they carried it inside the lunar module, it went airborne in the low gravity and just stayed there, drifting through the cabin like smoke that refused to settle. Harrison Schmitt, the only trained geologist to ever walk on the moon, developed what he called lunar hay fever within hours. His eyes burned, his sinuses swelled completely shut. He was sneezing uncontrollably in a spacecraft 384,000 kilometers from the nearest hospital. And every astronaut described the same bizarre smell: burnt gunpowder. Here's why that matters. On Earth, rock gets rounded, tumbled by water, wind, erosion. The edges wear smooth over time. On the moon, no wind, no water, no weather. Nothing wears smooth. 4 billion years of micrometeorites have ground the surface into a powder finer than talcum, but each grain is a tiny shard of broken glass, sharp at a level you can't see with the naked eye. NASA has a group called the Lunar Atmosphere and Dust Toxicity Assessment Group. And yes, that name is terrifying because it suggests someone thought this warranted its own task force. They found that the dust contains silicate compounds similar to the minerals that cause silicosis in coal miners, an irreversible, progressive lung disease. They also found nanoscale iron particles embedded in those glassy shards, chemically reactive in ways that organic tissue is completely unprepared for. The Apollo astronauts were exposed for 3 days with no air filtration and no sealed airlock. Artemis missions are planned to last weeks. The difference in exposure isn't linear, it compounds. But the dust isn't even the most dangerous part of being on the moon. The radiation is. Earth is wrapped in a magnetic field and a thick atmosphere. Together, they function like a planetary immune system, intercepting and deflecting most of the lethal radiation that streams through the solar system constantly. On the moon, neither of those things exists. Galactic cosmic rays, the stripped nuclei of atoms accelerated by ancient supernova explosions to nearly the speed of light, pass straight through the lunar surface, through spacecraft walls, and through your body with almost no resistance. As they go, they shred DNA strands. And here's the maddening engineering problem. Adding more shielding makes it worse, not better.
When a cosmic ray hits a thick metal wall, it shatters the atoms in the wall, producing a spray of secondary radiation, neutrons, gamma rays, charged fragments that scatter in every direction inside the habitat. The thicker the armor, the more secondary particles it generates. There is currently no known solution to this problem. The smartest aerospace engineers on the planet have been working on it for decades, and it remains officially unsolved. And on top of the constant background radiation, the sun periodically erupts in what are called solar particle events, unpredictable blasts of high-energy protons that can flood the lunar surface in hours. A major solar particle event could deliver a potentially lethal dose of radiation to an unprotected astronaut in less than a day. The Apollo missions were lucky. They flew during quiet solar periods. In August 1972, a solar storm hit that would have been catastrophic for any crew on the surface. It occurred in the gap between Apollo 16 and Apollo 17. It missed the astronauts by months. Not years, months.
Stay with me here, because this next part is the one that made me stop and actually reread the research twice. The moon is shrinking. Not metaphorically, literally. Its core is cooling, and as it cools, the entire body is contracting. Over the last few 100 million years, it's lost more than 45 meters of circumference. Now, on Earth, the crust is broken into tectonic plates that constantly shift and grind and absorb stress. The moon has none of that. Its crust is a single brittle shell, and when the pressure builds from the inside, it doesn't flex, it cracks. Sections of crust shove up and over adjacent sections, forming steep cliff faces called lobate scarps, some stretching for kilometers across the surface. NASA's Lunar Reconnaissance Orbiter has found thousands of these scarps. Many of them look geologically young, which means this process is still actively happening right now. And the cracking produces moonquakes. In 2024, a research team, including scientists at the Smithsonian, linked one of the strongest shallow moonquakes ever recorded, a magnitude 5 event, to a cluster of active thrust faults in the lunar South Polar region. The same region NASA has chosen for the Artemis 3 crewed landing. One of the candidate landing sites sits disturbingly close to an identified young fault scarp. And here's the thing about moonquakes that makes them different from earthquakes. On Earth, seismic energy dissipates relatively quickly. The ground shakes, the energy spreads, it's over in seconds or maybe a minute. On the moon, the crust is dry, fractured, and airless, so seismic energy has almost nowhere to go. A moonquake doesn't last seconds, it rings for hours, like striking a bell with a hammer and not being allowed to touch it. The shaking itself is gentler than an earthquake, but it goes on and on and on. And in a world where the surface is loose, unconsolidated rubble from billions of years of meteorite impacts, that sustained vibration can trigger landslides on the steep inner walls of craters. The very craters where we plan to drill for water ice, the ones that have never seen sunlight, the ones we know the least about. In 2025, just last year, those same researchers analyzed the Apollo 17 landing site and found that boulder falls and landslides in the Taurus-Littrow Valley had been caused by moonquakes, not meteorite impacts, as everyone had assumed. The fault responsible has been producing magnitude 3 events repeatedly for the last 90 million years. It may still be active. They calculated the odds of a damaging moonquake striking near an active fault on any given day at about 1 in 20 million, which sounds like nothing. Over a decade of continuous habitation, the kind NASA is planning, it becomes roughly 1 in 5,500. For reference, that's better odds than being dealt a 4 of a kind in poker. And as of early 2026, scientists have now cataloged over 2,600 of these compression ridges across the moon's surface, all of them formed by the same shrinking force. The cracking is everywhere. The faulting is global. But here's what none of the Artemis planning documents talk about in a single press release. Remember the footprint at the beginning of this video? The dust that clung to the boot and wouldn't let go?
Here's the part they didn't include in the mission briefings. On the sunlit side of the moon, ultraviolet radiation from the sun is intense enough to knock electrons off the surface of the soil. This gives the ground a positive electrical charge, and the smallest dust grains, the ones under a micron, the ones too small to see, pick up enough charge to be literally repelled from the surface. They hover. Some models suggest electrostatically levitated dust particles can reach altitudes of meters, possibly even kilometers, forming a thin, persistent layer of floating glass suspended above the lunar surface. On the dark side, the process reverses. The solar wind deposits electrons, giving the surface a negative charge that can launch particles even higher. At the boundary between light and shadow, horizontal electric fields may drive the dust sideways, a kind of permanent, invisible dust storm that never settles, never stops. The moon isn't just covered in dangerous powder. The powder is electrically alive. It coats everything it touches. It floats in the airless vacuum above the surface, and it may even partially obscure the view of the stars from the ground. Now put all of this together. You're living on a world with no atmosphere and no magnetic field, so radiation is passing through your body every second of every day with no known way to fully stop it. The surface is blanketed in chemically reactive glass shards that float on their own electric charge, penetrate equipment seals, and embed in lung tissue. The ground beneath you is the outer shell of a slowly cooling body that periodically cracks along active fault lines and shakes for hours at a time. The temperature outside your habitat swings 300 degrees every 2 weeks. And above your head, invisible particles of rock travel at 36,000 kilometers per hour, with nothing in the sky to stop them. The Apollo astronauts didn't encounter most of this, not because it wasn't there, but because they were gone before any of it had time to reveal itself. We spent the 1960s racing to plant a flag on the moon. We spent the decades after that learning what the moon actually is. And what the moon actually is a world that will tolerate a visit, but punish a stay. The ancient word for it was luna, and for a long time, in a lot of languages, it was also the root of the word for madness. Maybe they were onto something. If you made it this far, I genuinely appreciate you. Drop a comment and tell me, would you go? If someone handed you a one-way ticket to live on the moon, knowing all of this, would you take it? I'll see you in the next one.